right, let's start. So today we plan to talk about quantum field theory in dimension greater than 0. And here our approach will be as follows. We won't be attempting to develop a full-fledged axiomatic theory. Instead, I'll show you some examples and we'll discuss what the problems are and kind of whether in some cases one can get some interesting results. In other cases, one cannot. And basically, it was already the idea from the beginning of the course that our definitions are flexible, right? So now it will be even more so. So we'll have to be inventive with our definitions. Right, so Q of t in dimension greater than 0. So let's start with an example which is not really a Q of t. This is something that you know from the previous term, that's quantum mechanics. So it's a free particle. Now the dimension is equal to 1, right? This dimension is time. The action is given by the following formula. To t, so that's our Lagrangian of a free particle. Let me choose my space-time to be S1. So which means that this time is periodic, right? So then it's a bit strange, a universe, but well, that's how it works. Now, that's a one-dimensional particle. It moves on a straight line, right? So our goal to compute or define, to do something with the following quantity. Here, well, it's not quite quantum mechanics. To do quantum mechanics, instead of -1, one should put the imaginary unit, I. So this is more like statistical mechanics, but doesn't matter so much for our purposes. So, of course, this does not really make sense because of this d phi. It's not so clear what it is. Now, in the first example, I'll try to make some sense of it and fail. So let's see how it goes. So let me do the following. Let me look at this field phi. So this is a function on the circle. And as a function on the circle, let me assume that this is a sufficiently nice function such that it can be represented by a Fourier series. So if the length of the circle is 2 pi, then I can introduce the Fourier series for phi of t. So here, well, phi was a real valued function, so this would imply that the Fourier coefficients with opposite numbers are complex conjugate to each other, and phi 0 is in R. Sometimes in the physics language, this phi 0 is called the zero mode. So we'll see why. Well, now we can of course rewrite S in terms of Fourier mode simply by substituting phi n inside. And what we're going to get is something like this. 2 pi sum over n from 1 to infinity n square phi n square. And this is simply the Bessel's identity for this Fourier series. So we substituted in the integral over this circle, right? And that's what we get. So in particular, note that phi 0, this zero mode, it does not, maybe I should better write S of phi, it does not enter this decomposition. Right. So now let's at least formally try to write down an expression for z of h. And well, so that's this integral S of phi. And one naive attempt to make sense of it might be as follows. Let's say this is simply a product over integrals over various Fourier modes. Why not? And here I substitute the expression for the of the action functional. Well, at least, well, one cannot take it too seriously, but this, formally speaking, this integral factorizes over in the product of integrals. So let me write it in the following way. So of course, this is we can have doubts whether this expression makes any sense, and so all the expressions here are problematic, but they are problematic in a somewhat different fashion. So here we have an infinite product of integrals which actually do make sense, right? Each of them, it does make sense. It's just a Gaussian integral with some reasonable expression here. Obviously, their product perhaps does not quite make sense, right? So there is a difficulty here. And then there is another problem. So this integral over phi naught is just an ordinary one-dimensional integral. The problem is this is an integral over R of the function equal to 1, right? So this is not a very good integral. It's very openly infinite. So the idea in trying to make sense of quantum field theory, that, okay, there are two expressions. They're both very problematic. However, this expression is our friend. So this expression is not really our friend. So typically, what people in physics are doing, and one can, to some extent, make sense of it if one decides to do it. So one says that, well, this expression perhaps does make sense. So one can try to do something about it and kind of assign to it some value, maybe 1 or whatever. Treat it as some kind of number. So this expression, not really. Well, when you have a difficulty in quantum field theory, you invent a name for it. So the name for this situation is, so this is the simplest example of the so-called infrared problem, right? So this expression does not make sense. So basically, this Z of H does not make sense, and even the physicists would agree that this does not make sense. Here, one would probably have a disagreement with them, but here, so everybody agrees this is no good. So this Z of H does not exist, because of the infrared problem. And the infrared problem is this integration of over phi 0, which is just a number. And this is a one-dimensional integral over the real line. All right. So you see how it goes. We pose a problem. This is one of the simplest problems we can pose, right? So it looks like we play by the rules. We even agree to treat this thing as a kind of number, maybe, but still it fails. So this is one of the, just to tell you, this is one of the possible outcomes when we study quantum field theory. We're addressing a problem and we just fail. All right. So let's look, but then what's the strategy? Let's look at the next problem. Okay? So the next example would be, again, a free particle, but now let's put it on a circle. So the action is just the same. So the space-time is the same. However, the target space V will now be a circle instead of the real line. And let's assign it a radius capital R. So this means that we identify phi and yeah, let me use this convention. So phi and phi plus 2 pi r. So what's going to change? In fact, this expression is going to change, right? So now I'm looking for maps from a circle to a circle. And in particular, remember, we already had this discussion. There might be, so those maps may have non-vanishing degree. Right? So this means that all these expressions, so they are periodic, which means that phi, after going through from 0 to 2 pi, returns to the same point. Now, if we look at maps to the circle of non-trivial degree, maybe they don't return to the same point as functions with values in R. So let me instead write the following expression, and we'll see whether you agree. I claim that a reasonably nice function can be decomposed, again, in the Fourier series. However, there would be an additional term in general, and this term would be of the form R times W times X. So R is this R, or sorry, T. Instead of X, I should put the variable T. So there will be a linear term, and W is in Z. In fact, it's easy to see that W is a degree of phi viewed as a map from S1 to S1. I think we already had such considerations earlier in the course. So, you know, when t changes from 0 to pi, this expression changes by 2 pi r times this integer. And this means that this is a well-defined map from S1 to S1. So formally speaking, that's a map from R to R, but it descends to a map from S1 to S1. Right? Okay, good. Now the question is, how is the Bessel's identity modified? So you're replacing an integral over square of the derivative by some infinite sum. So how would it look like now? So you've got S of phi. So what's your guess? So how this formula, how does this formula change? Of course, probably the natural guess is that this term stays. Now, what's the extra term? Right now, I added some linear term here. So what's going to happen?
You take the derivative of this squared.
Yeah.
So it's r squared.
Yeah. So there will be like the length of the circle times the square of the derivative, which means times r squared times w squared. Right? So that would be the extra term. And why, just a test question, why there are no mixed terms which involve phi n and w? Yeah, well, does phi 0 enter?
Oh.
When you take the derivative of a constant, it's still 0. Okay, no worry about that. Now, why there are no terms which would mix w with those phi n's? By orthogonality in the Fourier series, right? Or what? So that's a constant term. So the derivative is a constant. So all the other terms, they come with those exponentials, so they are orthogonal. Very good. Now what about z of h? So what happens? Well, that's still this funny integral, which probably does not make much sense. Now, well, so there will be an integral over phi naught again, a product of integrals over d phi n, d phi minus n, or maybe I better put an integral inside. Right? Now, there is another parameter, this w, right? So there will be also sum over w in z. Now, what happens here? The integral over d phi naught is now from 0 to 2 pi r, right? So that's certainly very good news. This means that our infrared problem, at least in this way, it's gone, right? So it's a finite integral. Now, what happens here? So here we have exponential minus 2 pi over h r squared w squared. And I think I actually made a mistake. There is also a coefficient 1/2 coming from 1/2 here, which means that there will be just pi instead of 2 pi. And here there will be exponential minus, so that's the same as we had before, 2 pi over h n squared phi n squared.
This very first 2 pi is also the same.
Sorry?
And also s of phi is 2 pi plus. That also.
Sorry, 2 pi times.
Oh.
Right, sorry. Now I think it probably looks almost correct. Good. So now we decided at least for some time, to accept that this is some kind of number, z prime of h. In any event, if we accept that somehow this can be negotiated to be some reasonable meaningful number, it doesn't depend on r, right? So there is nothing. So this is whatever it is r independent. Now what happens with the r dependent parts? Well, we have 2 pi r solving our infrared problem times the sum w in z exponential minus pi over h r squared w squared. Right. So that's the r dependent part. So this looks very nice. So this expression, right, just a linear function in R. And I don't quite know. Probably many of you have already encountered such expressions in your mathematical life. So what is it? Is it? No. No. Right. How is it called? So let me recall. So Jacobi's theta function. So it's given by the following expression. So let me try to write a formula correctly. So n in z, and here exponential if I times n squared. Right. So this is an expression which is very important in number theory and in many other fields. So this is a function of tau. And you see, I mean, of course, here we have some i's, but tau is a complex parameter. So this expression is a particular value of this theta series or of the theta function. So if I'm not mistaken, in our case, so this is equal to z prime of h 2 pi r times the Jacobi theta function of what? Of I r squared over h, right? So we substitute this purely imaginary parameter, and then we obtain exactly this sum. So of course it's good to have a name, right? It's a fancy name, Jacobi theta function. But an interesting thing is that Jacobi theta function has the following extraordinary property. Sometimes it's called, let me copy it because I'm afraid to make a mistake. So sometimes it's called a modular transformation. So there is a relation between the values of the Jacobi theta function and the parameter tau and the parameter minus the inverse of tau. And so there's simply they're simply related by minus I tau to the power minus 1/2. So sometimes it's also called it's one of the versions of the Poisson resummation formula. It's a very surprising fact because you see, so we radically change this sum. We plan to replace tau by minus tau minus 1, right? So it's very strange. Here it was in the numerator, but in the numerator which was in the exponential. But then we rewrite it as a similar sum with tau being in the denominator. So it's a huge radical change in this function. Right? I guess many of you have already seen it at some point. Right. Okay, there we go. Now let's try to use this transformation here. So this is z prime of h times 2 pi r. And here, well, so we should write our minus I times I tau, which would give r squared over h to the power minus 1/2. And here we should write theta of minus the inverse. So here will be h over r squared, 1 over I. So I think this will give I again. So theta of IH over r squared. So maybe one more rewriting. So z prime h. So here 2 pi will survive. So what's going to happen here? So there will be r in the denominator. It will cancel the r here. And there will be h to the power 1/2. And let me rewrite again this theta series. Let me name the parameter in some other way. So k in z. And now I should substitute it again in the definition. So it will be exponential of minus pi h over r squared k squared. Right. So you see, it's also very interesting with this parameter h bar. So here in the sum, the parameter h bar was in the denominator of the exponential. After this Poisson resummation trick, or after I've used the modular property, it appears here in the numerator, right? Like maybe a test question for you. It's not strictly speaking in our course, but you had the course of quantum mechanics before. Now, physically, what you think about it? What does this theory say? What's the interpretation? What you think? What would a physicist say looking at this sum? All these k's, what are they, right? Is there some physical meaning to k's? So, you know, it's a particle moving on a circle, right? That's the physical system. Like, I don't quite know your quantum mechanics for mathematicians of a previous term. Would it cover a free particle moving on a circle? No, but you know, I know this student attitude, right? Kind of, did you learn something? No, right? Of course, that. So, physics interpretation. So we have a quantum particle moving on a circle of radius r. What's the difference? Like, what do you learn at school, or I don't know, or in quantum mechanics course? What's the difference between classical mechanics and quantum mechanics, right? Classically, a particle can move with whatever velocity it wants. What about quantum theory?
It's quantized.
Quantized in what way? So it's called, let's say, even before there was quantum mechanics, there was this Bohr-Sommerfeld quantization, which was saying that you associate a wave to a particle, right? So the particle, you associate a wave, and the wavelength of this wave will be something like h divided by the momentum of the particle, right? And if your particle is on the circle, you would want an integer number of wavelengths to be in the circumference of the circle. So otherwise, your wave wouldn't fit there, roughly, right? That's the idea. So this means that that 2 pi r divided by lambda should be an integer. So this implies the following. So if I use this Planck's identity, right, times 2 pi r is equal to k, and this means that P is h over 2 pi 1 over r times k. So in other words, the momentum is an integer proportional to 1 over r. Now, if momentum is like that, then the energy, let's say our mass is 1, so it's p squared over 2, and this gives us h bar squared divided by 2, and here k squared over r squared. So that's up to the factor of 1 over h and pi, which come from our normalizations. That's what you see here. So these are the expressions that you see here. So in fact, after this Poisson resummation, we obtain another expression for our partition function, and here we have the spectrum . So that's the spectrum of the quantum system. That's just for you to know how it works. So basically, maybe the first observation, so when we go beyond dimension 0, so quantum field theory, it resembles, mathematically it resembles number theory, right? Because we immediately go to some kind of number theoretic, interesting number theoretic functions. And so we can, in a somewhat non-trivial fashion, one should say, one can recover the information about the energy spectrum of our theory. And the energy spectrum, you probably learned in the last term that one should solve some Schrödinger equation, right? Or kind of whatever, some eigenvalue problem. Notice, I don't solve any eigenvalue problem. I just looked at the degrees of maps from S1 to S1, right? After that, I put them somewhat formally into this partition function, even though this part is quite well defined, right? So I just sum over degrees of maps. After that, I use the Poisson resummation formula or modular transformation for theta functions, and I get a spectrum of my theory. Right? It sounds a little bit surprising, kind of. At least it does not resemble solving the eigenvalue problem for some differential operator. Not really, but it's supposed to give the same result. So this perhaps gives you a little bit of an idea how interesting and surprising and mysterious quantum field theory can be, right? Now let's consider the next example. So this will be again a free theory, but this time this will be a free field, free scalar field. Free scalar field. Well, so M will be a domain of Rn, but sometimes Rn itself. V, again, let's take it to be equal to R. The Lagrangian, we know what it is. So 1 over n di phi squared dnx. Well, of course, the action is an integral of the Lagrangian. In this case, let me introduce the boundary conditions. So we'll discuss why they are needed, but let me choose something very simple. Let's assume that the space-time is a nice subset of Rn. It has a boundary, perhaps, and on the boundary, I simply put phi equal to 0. If this is the case, then I can do integration by parts and rewrite this expression as integral over m, sum from 1 to n. And here we'll have phi di squared phi dnx. Maybe one more rewriting. This is minus 1/2 integral over m phi times Laplacian of phi dnx, where of course delta is sum of the partial derivatives squared. Right? So that's the expression. That's the expression for our action. So let me compare it to the zero-dimensional field theory that we were considering before. So let me recall that they are typically S of phi would be equal to, let's say, if you don't introduce yet any interaction terms. So then for the Gaussian field theory, we will write it in the form like some quadratic, typically non-degenerate quadratic form. 1/2 is just a normalization coefficient. Or we would use some auxiliary scalar product, and we would write it as A phi. Right, where A now is an endomorphism of V. So these were writings of the action of a free field theory or Gaussian field theory in dimension 0. Now, how does it compare to this? How does it compare to this story? Right. So this expression is a quadratic form, right? So this is alpha of phi phi. Now, clearly, the operator delta is our operator A from this expression. And what is the auxiliary scalar product? Just an integral over m, phi 1 of x, phi 2 of x, dnx. So we identified the objects that we had with our free field, with our dimension 0 situation. Now what we're going to do, we'll be taking simple facts about dimension 0 and more or less try to interpret them as definitions in higher dimension. For instance, so we had Vix Theorem, which was saying that the integral over v exponential minus 1/2 alpha phi phi psi 1 phi psi k phi would be equal to, so what was it? 2 pi h to the power d over 2, determinant A, 1/2. Now h bar to the power k over 2, sum over matchings, a minus 1 psi I, psi sigma of I. So sigma is a matching. Right, that's if k is even and 0 if k is odd, right? So that's a good formula. Can we actually try to interpret it as a definition? So we attempt to write an integral over the space of fields. So here we have minus, oh sorry, there was also h here. So 1 over 2h, integral over m, sum over r from 0 to n, di phi squared dnx, right? And here we can write some kind of linear functions of phi. We'll discuss in a second what they are, and we would like to try to use this formula. So this would be now our definition. So for k even, there will be something interesting. For k odd, there will be 0. So the question is whether we can make sense of the elements that we find on the right-hand side. Right? So we need to, basically our plan is we need to say what kind of linear forms we will be allowed to consider. We need to make sense of this a minus 1, and we need to do something with the determinant of A, and we need to do something with D, right? So these are the problematic. So at least we need to give some interpretation to these questions if you want to use the formula as a definition. So I'll answer some of these, I'll discuss some of these questions, and I'll answer some of these questions after the break. All right, so let's continue. So here we have some list of problematic objects. So let's say something about their nature. So first, let's say what will be the linear forms. Well, one possible linear type of a linear form is just an integral of phi with some reasonably smooth function. Another type of linear forms which will be interesting for us, so they require so this requires more on the smoothness of phi, but we just choose some point x in M, and we just take a value of phi at that point. So that's an easy thing. Now, what about, let's take this a minus 1. So a, in our case, is a Laplacian. More generally, it might be some other differential operator. Typically, what we encounter in various field theories, so the operators A, which define quadratic forms, these are differential operators. And we would like to make sense of its inverse. Probably some of you may know well how it works. The others perhaps have never seen it. So have you seen inverses of differential operators? So typically it works as follows. In fact, differential operators, these are difficult operators from the point of view of functional analysis. That's because they are unbounded, and you have to define them on some usually their domain of definition is some complicated subspace of the vector space of functions that you're looking at. So that's what typically happens. So their inverses, or you can say quasi-inverses, we'll now see in what sense. These are usually very nice operators. Typically, the inverse of the Laplacian, let me take some function psi, are represented by integral operators. So there is some kernel. So an integral operator, and G is a function of two variables, so it's a function of on M cross M, and usually you should take away the diagonal, because we'll see there might be some problems. So minus the diagonal, so minus the set of points of the type XX to, in our case, R. In analysis, so the usual name for it is a Green's function. Or sometimes such an integral operator, it's called a Green's operator. So as I said, here the domain of definition of a differential operator, it's a major problem, because whenever there is not enough smoothness, then the outcome may be not defined, right? For integral operators, usually the domain of definition is all of your space. So this is usually not very critical. So one of the problems, you can say, is that this, so to say, inverse is usually defined on a much bigger domain. than the differential operator. Nevertheless, what we require so we want to, if we act by the Green's operator on the Laplacian or whatever, on A acting on something, we hope to get back psi of x. Right? And if you apply the Laplacian, let me write it, Laplacian in the variable x to the result of action of the differential operator, to the result of action of this integral operator, again we hope to get psi of x. Of course, for instance, here psi should be sufficiently nice so as Laplacian of psi should be defined. Here psi may be less nice, but typically the result of the outcome of the action of the integral operator is a nicer function. So usually, like when you differentiate, functions become kind of more and more nasty, but when you integrate, they become nicer and nicer, roughly speaking. Now, let me give you two examples of such functions. So first, something that you know from your high school course of physics and from many other sources. Suppose that we take n equal to 3 and the domain just to be R3. So what's the Green's function of the Laplacian in dimension 3? Who knows the answer? Please raise your hands. So 1/2? So I don't know how to interpret this sign.
Oh, this 1/2, yeah.
1/2? So nobody knows? Let me show you. You will recognize it immediately. So it's 1/4 pi. The Euclidean norm or Euclidean distance between the points x and y, right? And I think you've seen it at high school and other places. So what is it? So you take, for instance, an electric charge located at y, and you want to evaluate, right, the potential at the point x. So that's and that's exactly the solution of the Laplace's, or maybe more generally Poisson equation, which says that the Laplacian of the potential, right, is equal to minus the density of charge divided by something. So that we know from Newtonian gravity or from electrostatics. But that's actually, it turns out to be like in our math language, that's the Green's function defining the integral Green's operator, which is the inverse of the Laplacian. What about n equal to the same situation, m equal to R2? Any guess? Right, so we want to do electrostatics in R2. So what could it be? So that's electrostatics in R3. It could be here. Yeah, life is seldom that good. Sorry, 1? Yeah, so it turns out to be 1/2 pi, So that's similar to 1 over 4 pi, right? That was the area of a sphere over two sphere. That's the length of or area of one sphere. And instead of 1 over x minus 1, that's log of x minus 1. So these are concrete examples of how such operators look like. So as I say, in contrast to the differential operator, which is functional analytically, is a difficult and unpleasant object. So these are usually very nice operators. Even you see there is this singularity, which looks somewhat dangerous. But okay, we'll have difficulty with the singularity. But in principle, if you have a sufficiently nice function, then of course there would be no problem with the integration. Maybe check it that suppose psi is a smooth function, so then there is no divergence, there is no difficulty in integrating with such a kernel. All right. So what's next? So in principle, I should also discuss this, but this is hopeless, right? The dimension of our space is infinite. There is no way I can make sense of this h to the power d over 2. With the determinant, probably one can do something, but this is more complicated. We won't be doing it today. Instead, we'll discard this problem in the following way. So remember that there is a notion of a correlation function in dimension 0. And this is declared to be integral minus h s of phi, psi 1 of phi, psi k of phi, divided by the integral without insertions. Right, so that's just a definition. So this is the dimension 0 blackboard. Now, for the answer for a correlation function will be similar to this answer. The only thing is, so if instead of this integral, I write a correlation function, the only difference will be that I should cancel the Gaussian part, right? Now, if I cancel the Gaussian part, I no longer have any problem with interpreting the ingredients. So that's why if here instead of this, we would like to produce an infinite dimensional definition for the correlation function. So this seems to work very well. So let's write down the answer. So Vix theorem, but now it turns into definition. For free fields. So correlation psi 1 of phi, psi k of phi is equal to. Now it's 0 for k odd. It is h bar to the power k over 2 sum over matchings. And, well, here we write exactly the same thing as before. So a minus 1 psi I, psi sigma of I. for k even. Okay? So now that's a definition. Perhaps just to say, suppose we have xi and eta, some smooth functions on M. So in this case, this a minus 1 xi eta. For our Green's, for our kernel, so this will be an integral over M cross M g of xy, xi of x, eta of y, g and x, d and y. And we assume that if they are nice enough, then all the integrals converge. If xi of phi is equal to phi of x and eta of phi is equal to phi of y, let's say x is different from y, so then a minus 1 of xi eta will be simply the value of the Green's function, g of xy. So these are just particular examples of how it works. In particular, for instance, for n equal to 3, we can say phi x1, phi x2, phi x3, phi x4, right? So we can compute such a correlator. This will be 1 over 4 pi squared 1 over x1 minus x2, x3 minus x4, plus 1 over x1 minus x4, x2 minus x3, plus 1 over x1 minus x3, x2 minus x4. So this is just to show you that these objects are like nice functions. They are not scary at all, right? So it looks like our Vix theorem works very well. And we won't be doing it until the last lecture. But in principle, one can very well imagine developing the Feynman's theorem, right? So the Vix theorem, which now turns the definition, it looks very nicely, right? So the only thing was we needed to cancel this infinite, or possibly infinite prefactor. But so from here, that's a very good starting point for the Feynman's theory. And that's actually what Feynman did. So that's what he wanted to do in a much more complicated theory. Right. So now we'll choose for today a somewhat different route. And I'll show you. So I think already, like at the last hour, this Poisson resummation and the use of the Jacobi theta function was a kind of interesting thing, unexpected. Now I want to show you some other very, very interesting phenomenon which gave rise to thousands or maybe tens of thousands of research papers and which now constitutes one of the major research domains called conformal field theory. So before doing that, let me do one more exercise. So here we computed correlation functions of products of linear forms. So let me recall one more formula from the dimension 0 story. So, so there was this formula. So here we had minus 1 over 2h alpha of phi. And then I would add in the exponential. I would add in the exponential a linear form. Okay. So let me recall that the answer is So it's 2 pi h to the power g over 2, determinant a 1/2, and here exponential, I think, of h over 2 a minus 1 psi psi. So this was actually an element in the proof of the Vix theorem, right? So this expression. So I can also reinterpret it as the correlation function of exponential psi of phi, right? Now I should kill the prefactor. So this is exponential okay. So that's the formula. So very good. Now we do the same thing for free fields. I'll choose the dimension equal to 2. So I have an exponential of psi of phi equal to, well, exponential h over 2, and here a minus 1 psi. Well, now let's choose some concrete psi. So I would like psi of phi to be equal to sum over k from 1 to L phi of xk. So now I just need to evaluate this expression, a minus 1 psi. Well, clearly this will be sum over terms, k, no, L, sorry, may choose some other letter, let's say M. So sum over k and L, g of xk, xl. And let me recall that g in this case is 1 over 2 pi log of the distance xk minus xl. So this is from 1 to m. So it all works very nicely with the exception of one problem. What about the diagonal terms, right? Diagonal terms, they have xk equal to xl, and all those Green's kernels, typically they are not defined on the diagonal. Recall that we had to remove the diagonal. And now we know why, right? So if xk is equal to xl, it's certainly no good, right? Because it's a log of 0. It doesn't make sense. So in fact, this also has, so log of xk minus xk is equal to log of 0. And of course, this is no good. So the reason, kind of, as I said, whenever you encounter a problem, physicists have a kind of some fancy name for it. So this is called the ultraviolet. So that's called the ultraviolet problem, right? So that's clearly a problem again, right? It's simply does not make sense. Well, what's our strategy? When we encounter a problem, we need a new definition. So this definition was good, but now it kind of fails, right? So it does not make sense. Let me temporarily, for today, call it the physical correlator. So, right? So we kind of used our Vix theorem, but now we don't know what to do. So the idea is as follows. We simply simply throw away the terms that we don't like. We kind of don't know what to do if k is equal to L. Oh, let's just forget it, right? Well, that's a new nice definition. The right-hand side is now well defined. So let me do the following. Let me add a little bit of fancy stuff. First of all, let me add some arbitrary numerical coefficients. Why not? So this would modify the answer by having the product of those coefficients in front of G. And now I actually know what my I know what my Green's function is. So therefore I can actually rewrite it in the following way. So this is a product of k smaller than L, and here there will be xk minus xl to some power. So what's the power? The factor of 2 will be cancelled by symmetry, so there will be h over 2 pi alpha k alpha L. Right? So that's just what it is for the Green's function that we have here. So this is a nice function of coordinates on a plane. Perhaps one more remark before we do conformal field theory. Sometimes it is convenient to identify R2 with a complex plane. So, and then instead of xk and xkl, I will write zk minus zl. The absolute value of zk minus zl is still the distance between the points on the plane, and it is to raise to the power h over 2 pi alpha k alpha. So that's the expression that I would like to use. Well, now we would like to have a glimpse at conformal field theorem. Now let me start with an observation. Let me choose lambda a positive real number. And let me consider a transformation of this phi tilde of x, which is simply equal to phi of lambda x. Right, so I just rescale all the arguments. So let's look what happens with the action under this transformation. So, well, I should substitute, well, I can do it for general n, but later on we'll specialize to n equal to 2. So this will be gi phi tilde dnx squared. Well, So what will it be? This will be 1/2 integral. So integral over Rn, right? Sum from 1 to n. Now what happens here? When we differentiate, we get an extra factor of lambda, and this is di phi of lambda x that we're getting there. That's our differentiation. We differentiate phi tilde, we get an extra lambda. I get a square here. Now let me do it, sorry, let me do it for n equal to 2. And then, well, let's discuss what happens for other values of n. Okay, very well. I obtained this expression. Now let's do the change of variables. Let's rescale, let's replace lambda x by y. So then, of course, you will have a Jacobian of this change of variables, which will be lambda to the power minus 2, right? Because we are in dimension 2. So this will give us 1/2 integral over Rn. So the Jacobian is lambda to the power minus 2. Jacobian times lambda square, which comes from here, times sum 1 of n di phi of y squared d2y. Well, the factors happily cancel, and we obtain s of phi. Right? So s of phi tilde is the same as s of phi if we do this rescaling. Now, maybe like before we proceed, just a test question. What would happen, like I kind of, on the way, I change the dimension from n to 2. What if I do it in arbitrary dimension n? If I continue the calculation, would I still find s of phi tilde equal to s of phi? In general, no, right? So there will be some factor of lambda. Can I save it in some way by changing this formula? Yes. Yes, right? So suppose now we put back n. Right? So here, yes, here we put back n. So here then, in general, it would be lambda to the power minus n. So here we still get lambda squared. So we need to compensate the difference somehow. Where would the difference come from? I think we need to add here lambda, right? If I introduce such a factor there, then they would again exactly cancel. Now that's, so this is called the scaling dimension of phi. Sometimes we like, I think the notation would not be very good, but okay. And notice that exactly when n equal to 2, the scaling dimension vanishes, right? So we don't need to introduce any extra factors to preserve the action. For n equal to 2, n over 2 minus 1 is exactly 0. So the scaling dimension vanishes. Now, so here is our expectation. So the scaling doesn't change the action. So we hope that the correlation function right? It's a function of z's. z1 to zn. Right? We expect that if we scale them, the correlation function wouldn't change. that's what we expect. Why is that? That's because those correlation functions, right, they're defined as integrals with the kernel given by S. S doesn't change when we scale. So then the hope or the expectation is that there would be such a law. Now we can easily check whether this is true or not, because we have a very explicit and very simple expression for the answer. Right? So we can just make a substitution. So we take the correlation function with scaled arguments. To the power h over 2 pi alpha k alpha L. Well, this is equal to lambda to some power. And here we have a product k smaller than L, zk minus zl to the power h over 2 pi alpha k alpha L. So that's the original correlation function. Now what's the power? Let's just count. So this will be the sum over k smaller than L, h over 2 pi alpha k alpha L. Right? So that will be the power. First of all, observe, since alphas were arbitrary numbers, in general, for sure, this is not zero. Right? So this is an interesting news, to some extent maybe at first a bad news, but like something which would be true in classical theory is no longer true in quantum theory. So we had a symmetry of our classical theory, but this is not a symmetry of the corresponding quantum theory. So for that, as usual, there is a name. Right? So this is called an anomaly. Right? So quantum theory has a different features from the classical theory. So in particular, this is the conformal anomaly. Now let's study in more detail this expression. So h over 2 pi sum k smaller than L alpha k alpha L. Let me rewrite it in the following way. So this is h over 4 pi sum over k alpha k squared minus h over 4 pi sum over k alpha k squared. Is it true? Let me first make a simplifying assumption. Assume that the sum of alpha k's vanishes. So then the result allows for the following interpretation. That the expression exponential of phi lambda z, remember we had here the product of exponentials of alpha times phi lambda. Let me put here alpha. Scales, whatever that means. The scaling dimension in that sense, which is equal to minus h over 4 pi alpha squared. So you see, we're saying that we study the expression exponential alpha 1 phi z1 exponential alpha m phi of zm. We make a scaling transformation of these, and it turns out that it will be accompanied by multiplying this expression by this factor lambda. So this is a very, very surprising, very strange phenomenon. And this is a cornerstone of conformal field theory. So you have this anomaly, but this anomaly allows for an interpretation that now this exponential, so this guy, it seems, doesn't scale. So you see 2 over 2 minus 1 is 0, right? It shouldn't scale. It shouldn't behave in any kind of strange way when you make a scaling. But in quantum theory, it does behave in that way. So this is called the anomalous dimension of exponential of alpha phi of z. Notice that if you take just phi of z itself, it behaves normally. Nothing was happening to it. When you put it into the exponential, the quantum theory predicts, or quantum theory, our definition, right? Our very naive definition predicts that there is an interesting scaling behavior. And as I say, like this small observation, in some sense, it developed into thousands and tens of thousands of research papers. So there is an approach how you think about it in terms of algebra, how you think about it in terms of probability theory, and how you do it in more complicated models. But that's the easiest model, the free field, right? And so the phenomenon is here. Now maybe let's finish with the discussion of what if this is not 0? Suppose that the sum of alpha k's is not 0. So then you have an extra expression of this form. But notice that it actually resembles the other expressions, right? So let me call this guy alpha 0, right? So this expression resembles the other expressions, only it has an opposite sign. Any idea what this might be? So this looks also very beautiful, somewhat surprising perhaps. So the interpretation of alpha 0 is as follows. So up to now, I was telling you we study quantum field theory on a plane R2 or on a complex plane. In fact, the formula tells us that maybe we are wrong. So one can think of C as an open dense subset in CP1. So in fact, the formula tells us that maybe secretly we study the theory. So here our points Z1 up to Zm. But maybe we study the theory on CP1. And secretly we have one more exponential of a linear form sitting there. So we have exponential alpha 1 phi of Z1, exponential alpha m phi of Zm, and we have exponential minus alpha 0 phi of infinity. So why infinity? That's because how does it work in complex analysis when you want to consider the neighborhood of infinity? So we have a transformation, z goes to lambda z, right? We have a scaling, z goes to lambda z. So if you want to look at the neighborhood of infinity, we should introduce a new variable, for instance, 1 over z, right? So what happens to this variable? It goes to 1 over lambda z, and this is lambda 1 w. It has the opposite scaling, right? So this guy has the exponent alpha 0. Well, we do encounter h over 4 pi alpha 0 square, but there the scaling is the opposite scaling, right? If we're sitting at infinity, if we're expanding, it would be contracting there. So that's the interpretation of this factor. So in fact, this is a function which is defined on CP1, and it has, or tensor, better say tensor defined on CP1, and that's the transformation of this tensor under those scaling transformations. So in one of the exercises, I'm asking you to look at the fractional linear, the Möbius transformations, and see how it works for them. So much for conformal field theory. That was short. But so next time we'll be doing abelian gauge theory. Also a little bit in this style. I'll show you some interesting things about abelian gauge theory. These are more definitions than theorems, but that's how it is. So yeah, let's have a break.